Hey Chemstars, this is Mrs. Vanderwall bringing you another Chemstar video. We are still in Chapter 5, Section 3. We are still talking about periodic trends and periodic properties, okay? And so the last video, we talked about attraction and we talked about atomic radii. Well, this video is going to be about ionization energy. And what is ionization energy? I'm glad you asked. It is the energy required to remove an electron. So the question is, how is this related to attraction? Remember how I told you how everything was related to attraction? So how is this one? Well, let's go back a few slides. Do you remember this? All right, this was all about attraction, wasn't it? And what did we say attraction was based on? Two things. If you're going across a period, it's all about the number of protons. If you're going down a group, it's all about how far away you are. So if ionization energy is the energy required to remove an electron, remember that was me. So how is it going to be harder to pull me away from Harrison Ford? If there's one Harrison Ford or if there's 4 or 10 Harrison Fords? Well, obviously the more Harrison Fords, which remember is my proton, the harder it is to pull the electron away, me. All right, why? Because it's greater attraction. So the more attraction, the more energy is going to take to pull me away. Well, what if I go further and further down a group? Remember what's going on as I go further and further down a group, I'm getting further and further away. So how hard is it to pull me away from Harrison Ford if I'm already pretty far away? Well, not too far, not too hard at all, is it? So it's going to be hardest to remove the electron up here, all right, because it has fewest shells and it has more protons. So if I'm looking at hydrogen and helium, it has helium has the same shell as hydrogen, only one, but it has 2 protons versus hydrogen's 1 proton. So I would expect hydrogen to have the greatest ionization energy, and then francium to have the least. Why? Well, francium's outer electrons are furthest away, 7 groups down. All right, and it has the fewest relative number of protons. The relative nuclear force there, if you will. Okay, so yeah, so that's how attraction is related to ionization energy. So let's go back to where we were. So let's put into words, how is ionization energy related to attractions? All right, well, the more attracted it is, the harder it is to remove. Okay, so the more attracted the electron is to the nucleus, the harder it is to remove. So if I'm going across the period, I have more protons, so I have more attraction, so I have greater ionization energy. So what if I go closer to the top? What's happening as I go closer to the top? I have fewer shells. It's closer to the nucleus. So I have greater attraction, therefore I have greater ionization energy. So do you remember what I said? Which element is going to have the highest ionization energy? We'll just take a look at the first few of these. Look at these numbers. Which one is the biggest number of all of these? Isn't it helium? Isn't that what I said earlier? Why would helium have the greatest ionization energy? It's because it has the fewest shells, 1. So between hydrogen and helium, which has 1 shell, it has the most number of protons. Okay, so as I go across the period, that's what this is, hydrogen, helium, let's go across a period. Lithium going down to neon, that's a period. What's happening? The ionization increases, you have more protons, more attraction, harder to remove. Look at these numbers. They don't lie, do they? Okay. So what happens if I go down a group? All right. So let's look at hydrogens in group 1, lithium's in group 2, sodium's in group 3, potassium's in group 4. What's happening? I'm going from 1,312 to 520 to 496 to 419. It's going down, isn't it? So as I go down a group, it's decreasing. Why? I have more shells, it's further away from the nucleus, I have less attraction, so it takes less energy to remove me, all right? And so I actually wanted to change letter C, all right? I want to change letter C. It says, why does the ionization energy decrease with, let's make it nitrogen and oxygen? Look at this right here. Here, let me circle this. All right, let me circle this. Here's nitrogen, and here's oxygen. Do you notice that there's a dip? And there's a dip here too between phosphorus and sulfur. Why is there this little dip? Look at these numbers. Aren't they going up? Yeah, more protons, harder to remove, but oxygen goes down and then it goes back up again. Yeah, but over here, look at this, look at this. The ionization energy is going up. Yeah, more protons, more attraction, harder to remove. But wait a minute, I get the sulfur. Oops, it goes down. Why is that? Well, let me tell you, okay? What we're going to do is that we are going to look at its orbital notation. So what I have here are nitrogens and oxygens orbital notations. So here's nitrogen, this is my 2s2, my 2p3. Do you remember talking about that? Oxygen's 2s2, 2p4. So why do you think? Let's think about this. So here's nitrogen with 7 electrons, all right? And this is my last electron. I'm going to pull it away. So how much energy does it take to take this out of its shell? Well, it's going to take, let's go up. It's going to take 1,402 kilojoules of energy, all right, to pull this away. But why is this one right here? Why is this electron easier to remove? It's paired up, isn't it? It's paired up. So there's more electron-electron repulsion. If there's more repulsion, it's easier to remove. Not by a lot, because I do have an extra proton, but enough to make that little dip. All right, so it is slightly easier to remove an electron that is already paired due to electron-electron repulsion. So there is no other electron to this, all right, so I can remove it, it takes more energy. But there is an electron already bonded, to this, so it's slightly easier to remove it because of the electron-electron repulsion between those two electrons. Okay, so I just want to show you there is some dips and there is some, changes here. So if I look at this chart, all right, and you notice there are dips. Just check out the dips. All right, there's a dip between barium and boron. Here's their nitrogen, oxygen. There's a dip between magnesium and aluminum. And again, phosphorus and sulfur. All right, and then there's a dip between zinc and gallium. There seems to be these dips when we go from the S to the P, from the half-filled shell to the next, electron added to it. So it's not a perfect trend, but I think you can still see it. All right, so the question is, which element in period 2? All right, so let's circle, or let's figure out what period 2 is. This is my period 2. So of these elements, which has the lowest ionization energy? Well, the one down here, it's lithium. Why? It only has 3 protons compared to neon's 10. Which one has the lowest ionization energy in period 3? All right, let's look at period 3. Here's period 3. All right, so which one is it? Yeah, hopefully you got it. It is sodium. So what's happening? As I go across a period, what generally happens? All right, I said generally increases. As you can see, there's dips, but overall it goes up. That's what you need to know. So as you go down the group, well, let's see, where's a group? All right, let's use me the blue. So here is the group, and here is a group. So in general, what's happening, it slightly goes down, doesn't it? It slightly decreases, okay? It does go down. So will barium have a greater or smaller ionization energy than cesium? So here's cesium. Barium has the very next atomic number. It's not on the chart. So would you expect this to keep going down, or would you expect it to start coming up? Cesium is the first element in its period, isn't it? Oops, I thought I had periodic table, I guess not. So what would you expect barium to do? It's going to go up, isn't it? It's going to have a slightly greater ionization energy than cesium. Why? It has 1 more proton, more attraction, harder to get rid of. So what about francium? Francium's on the chart, but francium is the lowest one on the periodic table in group 1. So it's right underneath cesium. So what would I expect francium to have? A smaller, easier to rip off, all right? So then it says, hypothesize why zinc has a greater ionization energy than gallium. All right, here's zinc, here's gallium. All right, so I wrote this. Where is zinc? Zinc is in the third shell. 3d10, all right? If it's in the third shell, it's actually closer to the nucleus than gallium, which is in the fourth shell. It's further away from the nucleus, so it's a little bit easier to remove, all right? That's why gallium is at a lower energy. It takes less energy to remove it from a 4p than a 3d, okay? Let's go to the next page. All right, so here's our summary. So the question is, which one has a greater? So let's talk about greater. If it has a greater ionization energy across the period, all right, why? Well, it has more protons, more attraction, therefore harder to remove, all right? I'll give myself a little room here. So what if I go this direction? Okay, it has fewer shells, closer to the nucleus, more attraction. I guess I have to scooch it over. So it's harder to remove, all right? So if I'm going this direction, and if I'm going this direction, which element has my greatest ionization energy? Yes, it is helium, isn't it? Which one has my least? Well, right now it's francium, okay? So to answer these questions, really the question is, which one's closest to helium? That's what's going to give you the greater ionization energy. Once again, has the most attraction. It's going to be harder to remove the outermost electron. So if I'm looking at lithium versus fluorine, well, which one is it? Hopefully you said fluorine. Why? More protons, more attraction, harder to remove. How about fluorine or iodine? Which one do you think it is? Yes, it is fluorine. All right, why? Has fewer shells, more attraction, harder to remove. All right. Oops, actually I forgot, this is my relation between lithium and fluorine. Here's my relation of fluorine and iodine. So what about barium and sulfur? Hey, we're going into that diagonal again. All right, so which one is it? Well, which one's closer to helium? Sulfur is. So why? It has relative more protons, so it's a greater effective nuclear charge, and it has fewer shells, okay? So what I would like you to do, all right, is let's take a look at this one. So you work on this. So sodium, which is right here, or oxygen. Which one do you think it is? Go ahead and answer that right now. All right, I said it was oxygen. Why? More relative protons, so great effective nuclear charge, and it has fewer shells. So if it's in this diagonal, always go the one towards helium, okay? What about beryllium and barium? Here's beryllium, here's barium. Which one has a greater ionization energy? Go for it. All right, hopefully you picked beryllium. Why? Because it's higher up, fewer shells. Okay, what about argon or fluorine? Here's argon, here's fluorine. Again, I'm going to try to stay away from when the diagonal goes this way, but as it turns out, it is going to be fluorine. All right, well, why? Fluorine has fewer shells. Okay, what about the next one, copper or radium? Well, where's copper, where's radium? Here's radium, here's copper. Which one's going to have a greater ionization energy? Go for it. Hopefully you picked copper, yes. So iodine or neon. Here's iodine, here's neon. Hopefully that's a no-brainer. Which one's gonna have a greater one? All right, did you pick neon? Yes, it has more relative protons and fewer shells. It's more to the right. That's what I mean by relative protons. What about potassium and vanadium? All right, they're in the same period, folks. Here's potassium, here's vanadium. Which one's going to be harder to remove? I hope you pick vanadium. Has more protons, more attraction, harder to remove. What about calcium or francium? Here's calcium, here's francium. Well, duh, don't pick francium. What did we already say? All right, here is the least ionization energy. So I would say calcium because it has fewer shells, closer to the nucleus, greater attraction, harder to remove. What about tungsten and selenium? All right, here's tungsten, that's the W, and here's selenium. Okay, so which one is it? Tungsten or selenium? Hopefully you picked selenium, has more relative protons and fewer shells. All right, what about silver or zirconium? They're in the same period. Here's zirconium, here's silver. Which one is it? Oops, silly Mrs. Vando, I put the circle in the wrong spot. It is silver, has more protons. I knew that. All right, what about the next one? Fluorine or francium? Well, hopefully that's a no duh. Go for it. It is fluorine. You are correct. Well done. So I'm going to leave us here because the next two trends are very, very similar to one another. So I want to do those together. So I'm going to leave you here. So don't wait to be great. We'll see you next time. Bye-bye.